Let's start off by answering the question, which activation function is the best? And I have here a list of a bunch of activation functions. And let's go through them in historical order. So if you just have a linear layer, you're basically doing linear regression. That's kind of the same as doing linear regression with identity function as your activation function, right? In other words, no activation function. This is not doing anything at all. Linear regression was first because Gauss and Legendre were doing it back in 1705 or whenever they first published it. So I guess identity is the first activation function. Now, if you remember last time we showed a proof that if you have a 3-layer neural net with 2 linear layers and 1 nonlinear layer, then you can approximate any possible function. You remember that? Okay. To do that proof, I used tanh. I'm getting ahead of myself. The next activation function that got really big was binary step. This is pretty much because, well, that has to do with perceptrons and because people used to assume that everything in computers is binary because everyone knows computers do ones and zeros, right? So they wanted to kind of bridge between computers and brains by building these things called perceptrons, which developed binary output values. And we'll talk about how that has to do with the activations of neurons in your brain a little bit later in the class. But binary step was used for a while until people realized that you couldn't train them with gradient descent. Why? Yeah, this isn't differentiable. So people switched to logistic function. Logistic function is basically a smoothed out version of binary step function. And logistic function was a popular activation function for several years until people came to the realization, hey, if it's centered at the origin and approximates identity function at the origin, that's a nice property, especially for initializing the weights, which I'm planning to talk about today. So it turns out tanh and logistic are the same function. A lot of people don't realize that. If you just take the logistic function and you stretch it to be twice as tall and twice as wide and scale it down a little bit, it is the tanh function, exactly. So these are just two different ways of presenting the same function. Or in other words, they differ by a linear transformation. People have sat on tanh for a long, long time. Now, of course, people decided to try lots of other things. So arctan, soft sine, inverse square root, all these things are random activation functions people have tried and found that, yes, they work. But pretty much everyone just sat on tanh. Tanh was very popular, did a pretty good job, and has some nice properties. Rather recently, rectified linear, or rectifiers, which when attached to a linear layer become a rectified linear. I just call them rectifiers. This is a very simple activation function. And oddly, it works really, really well. And there's a bunch of empirical results to justify that. And so rectified linear became super popular in the last few years, and everyone's jumping on the rectifier bandwagon. People found if you make them leaky, meaning you make them, instead of flat out less than 0, you make them bend downward a little bit. That works too. Turns out leaky rectifiers do a little better than rectifiers in most tests. Yeah, basically you just wave your hands and make it go away. The truth is you cannot differentiate at exactly that point, so we just pretend it's on one side or the other and go with it. Think about it this way. If you pick a random number, what are the odds it's going to be exactly 0? 0 officially. Yeah, it'll actually be somewhat greater than that with computers because there's not an infinite number of compute numbers the computer can represent. But it'll never be exactly 0. Or if it is, well, how bad is it going to screw something up if you change it from 0 to 0.000000000000001, right? It's kind of the same number, so we just ignore that problem. However, if you look at this chart, you'll see some people worry about it because there's this continuity column here. And, okay, I'll admit I added that column, but I worried about it once. So some of these activation functions have total continuity, some of them don't. And if it bothers you, you can... Wait, why is identity in there twice? What? I changed it? I didn't edit it. Huh. Oh, I clicked on one of those things? Ah, now I'm all lost and confused. Where am I? Okay, well, here's a point I want to get to. Remember our proof that if we had some set of points, we could, if we wanted to, fit a tan H shape in between them all, and then sum together a bunch of tan H's until we've perfectly hit all the points. Does that work with other activation functions? Let's suppose instead of tan H shape, we had rectifier shapes. So can that shape work?
You have to flip the ranges, right? That one has like negative infinity to 0 and 0.
Yeah, so assuming we can take any shape we want and we can stretch it horizontally and stretch it vertically and translate it horizontally and translate it vertically, basically it doesn't really matter what the shape is. There's some way that if you added a bunch of them together and stretched them in these ways enough, you could make them go through any endpoints that you could possibly come up with. And it's actually provable that any activation function can, in theory, work. And by work, I mean satisfy Cybenko's proof that if you have 3 layers, 2 linear layers and 1 nonlinear layer, you can arbitrarily fit any data with arbitrary accuracy. Does that make sense? So in theory, which activation function you should use, it doesn't matter. In practice, which activation function should you use? Take your data, do cross-validation, try them all. Whichever one yields the best accuracy in cross-validation, that's your best bet. Lately, people are leaning heavily towards rectifiers, wherever they are. I like leaky rectifiers. One of my grad students recently did a comparison of them all. He found exponential, where is it? Everything's confusing because they're all out of order. Let me just refresh the page so they're in the order I'm used to.
You can click on name.
Ah, okay. He used exponential linear units and found that they outperformed most of the others for a lot of his tests. Until we tried a variation of this one, which we have yet to publish, and found that it actually beat that one. So the best one will soon be published. Just wait. Of course, somebody else will come along and come up with yet a better one. In the end, here's the real message you should take. Doesn't really matter. Just pick one, go with it, you'll be fine. For this assignment, let's all use tan H because that way we're all on the same page, unless you don't want to. If you want to use a rectifier, cool, give it a shot. I'll work with you.
We use the stochastic gradient method?
Yeah, we're going to use stochastic gradient descent to train it, just because that's what I'm teaching today.
How do we choose the learning rate if the pen?
Sorry, what's that?
Choose the learning rate?
How do you choose the learning rate? Good question. Here's the general answer. Try a bunch of learning rates, do cross-validation, whichever one yields the best result, that's the best one. That's going to be my answer for every question you guys will ever ask me. There's a good one. Use that one.
Wouldn't a small learning rate always be better though?
So, that's a good question. What's the optimal learning rate?
Little learners are better.
So, well, let's suppose you have a nearly convex surface. And even if you have a really crazy surface, if you zoom in close enough, they're pretty much going to be smooth, right? So if something works with a kind of bowl shape, it's probably going to work in general. That's kind of a weak reasoning. But if your learning rate is too small, here's what will end up happening. You will go from here and go hop, 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 bum, 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 till you get to the optimum. Problem solved, right? Let's suppose your learning rate's too big. You might jump way across there, jump way across there, jump way across there, ching, 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 and then problem still solved, and hey, you still found the optimum. So that's not really such a big deal. Let's suppose your learning rate is way too big. Well, then you might actually make things worse. And then, oh no, I fell off the edge. That doesn't happen, but so it's important your learning rate is not too big. If you don't want your learning rate to be too small, because if it is, then it'll take a darn long time to get to the optimum. So not too big, not too small. You want to be right in the Goldilocks zone. Where is the Goldilocks zone? I don't know. I like 0.03. Here's why I like that number. Because for years, everybody recommended the learning rate should be 0.1. And that worked for most problems, except sometimes it didn't work because it was too big. And so I said, well, hey, let's just make it a little smaller. So now I recommend to my students use 0.03. And I haven't yet found a problem where that doesn't work well. Sometimes I've gone as low as 0.01, but it's always a little bit slower than 0.03. So 0.03 seems to work. Give it a try, and there you go. That's actually not a great answer, and I just lied. I have found problems. I found a problem where I had to have 1 times 10 to the negative 7th before it actually worked. That was a really deep network, and it had all kinds of local or really chaotic surface. Imagine if you had a decaying learning rate. So what if your learning rate starts off crazy big, and then it got a little smaller, then a little smaller, and a little smaller, and a little smaller, and then pretty soon you're going like that, taking little tiny baby steps. Seems like that would do a good job, right? Turns out decaying your learning rate is a pretty good practice. Usually yields good results. You don't want to decay too fast because you don't want to take a step, take another step, take another step, and then basically get stuck right there, right? So don't decay all the way down to 0. How do you pick a good decay schedule? There's all kinds of things to do with that. We'll talk a little bit more about best way to optimize that. There are new papers that have come out about dynamically tuning your learning rate, and there's cool approaches that do that. There's a few different techniques you can use. For this assignment, I say just use 0.03 for your learning rate, or maybe 0.01 if you prefer, and just train until it converges, and that should give you great results. I don't think you'll need anything more fancy than that. So there's the answer to your question.
So on your code, how many epochs do you need?
How many epochs do we need? Let's answer that question. By the way, I'm just going to poke in a few quick answers, then I'll answer that question, or a few quick statements. I was forced to change my office hours because a bunch of other faculty members could only meet at 11 o'clock, and I had to go to this meeting. So instead of Thursday from 11 to 12, I changed it from Thursday to 12:30 to 1:30. I apologize for anyone who that is inconvenient for. I am happy to schedule different times with you if you want to send me email, but there's my new office hours for now. Other point, qualifying exams are coming up. Does anybody have multiple qualifying exams and is getting slammed by that? I know they can be kind of high stakes, so if you have multiple qualifying exams and my assignment 2 is causing you to stress about should I choose between this class and succeeding in the program here, I can bend some due dates for you. I'm not going to bend the amount of work you have to do. I'm just going to make yours pile up more at the end rather than at the right now. But I have let at least one other student move those due dates due to the qualifiers, and I have to be fair. So if you are in that situation, do let me know. Okay. Okay, those were my 2 points of business. Remind me what your question was again.
So how many epochs do you need to run, and how fast is that?
How many epochs does it take? I added this information a couple weeks ago, 3 weeks ago, something like that. some of you have browser caches that cause your web browser to remember my instructions from before and not get the updated instructions. So just to make everything go smoothly, if every once in a while you'd hold down your Shift key and press the refresh button, that'll make sure you always have my latest instructions, and that empowers me to update them as needed. I added this stuff here. This is the output of my implementation of this assignment. I trained for 0 epochs, and then I measured my accuracy against the test data, and I achieved 9,243 errors. This actually makes sense. You should get about 9,000 plus or minus a little errors on the test data. Here's why. There are 10,000 patterns in the test data. There are 10 digits, 0, 1, 2, 3, 4, 5, up to 9, right? And there is equal representation of all 10 digits. So if you were to take a random neural network, initialized with random weights, it would basically make random predictions, right? Or possibly it would always predict the same digit, whatever one it is. Well, if in 10,000 testing samples, you get, how many would you get right with random guessing? 1/10, right? So that means you should get 90% of them wrong. What's 90% times 10,000? Should be 9,000. Well, in fact, I got 9,243 errors on a randomly initialized neural network. What does that mean? It means my random initialization was a little bit worse than it needed to be. Maybe I should have picked randomly again. I probably would have got 8,000 something errors. But it should start at about 9,000. After one training epoch, I was getting 600 errors. What is an epoch? That means for every pattern in the training data, I have presented it to my neural network and updated the weights one time with stochastic gradient descent. We'll talk more about that today. So by 2 epochs, 3, 4, 5, 6 training epochs, I had 337 errors. Now, each epoch took about a minute on my computer, if I remember correctly.